All right, today we're going to talk about the Rae Glycol chiller. We're going to cover some chiller basics, kind of touch on the different versions, startup, and then some helpful tools and helpful links that are out there. First, we're going to go over some chiller basics. What a chiller does is utilize an intermediary or secondary heat transfer fluid. Think of water or water plus glycol, which is an antifreeze. This fluid, transfer fluid, is cooled via direct expansion, DX refrigeration, and is pumped to a heat source. Think AC, display cases, walk ins. One part of this is there in the secondary fluid, there's no phase change or latent heat exchange in the secondary fluid. It is exclusively sensible heat. Now, it's broke up into two separate sections. The primary side, that's the standard refrigeration cycle using traditional refrigerants. And then the secondary side, that's the glycol system. And then, again, an important call out is there is no phase change in the secondary fluid in the glycol. We're going to go over some applications, operations, and components. Applications, chillers are typically used on larger sites like college campuses or large apartment buildings. And they're used there because they tend to be more efficient. And as you scale things down, they become less efficient. So then why are we using these chillers at all? Main reason is main reasons are government compliance, safety, and then client initiative. So we're trying to reduce our refrigerant charge for government regulation. Then we're trying to get it out of the conditioned spaces. And then some clients, they have zero emissions initiatives. So they're trying to get away from traditional refrigeration, traditional DX refrigerants. So some of the refrigerants that can be used are either toxic or flammable. And what we're doing by getting it out of the space is isolating those refrigerants from the point of use. The primary use of these chillers that we're going to be talking about today is for medium temp display cases and walk-ins for grocery stores. But you can use a chiller in comfort cooling. So, operation, it is set up in two separate systems. Our primary side, that's our DX side, and our secondary side, which is our glycol side. I'm not going to spend very much time on the primary side. That's our traditional DX, in this case, rack refrigeration. But primary side is going to be the rack where the evaporator is a plate heat exchanger that chills the glycol. So then we get our glycol that's chilled. It's chilled inside of a plate heat exchanger. It is physically separated. So we have DX refrigerant on one side of a plate and glycol on the other. These two do not mix. Once that glycol is chilled, it is pumped around the store and picks up heat in the cases. Then inside of the cases, the traditional evaporator that we're typically seeing is a heat exchanger where sensible heat is the only way we transfer heat from air to glycol. There is no latent heat or phase change that occurs in the glycol. Glycol does not change state. That is a big deal here. Now, again, to reiterate, the secondary fluid, the glycol, is chilled by the rack, pumped into the store where it picks up heat from inside of the store and is pumped into the heat exchanger where we exchange heat between the rack refrigerant, and the glycol. Our components on our traditional DX side, it's going to be our compressor, condenser, expansion valve, and evaporator. We may or may not have an EPR, and what we're going over with today has EVs, and then our secondary side is our glycol side. Those components are going to be our plate heat exchanger, the heat transfer fluid itself, 35% propylene glycol, pumps, the entire fluid distribution system, different controllers, and then some flow control valves. So the plate heat exchanger, it's where the DX side and the heat transfer fluid meet. This is basically this is a large evaporator for the rack. In this application, it's called a chiller. These glycol skids, these Rae glycol skids, they're utilizing a brazed plate heat exchanger. We often see these on mechanically subcooled racks, but this one is larger and it may be the only load on the rack. This style heat exchanger, there's a series of plates fused together with small gaps between those plates that keep the glycol and DX refrigerant separate, but in close proximity. The heat can be exchanged between them. Next portion is our pumps. What they're doing is creating a pressure differential to move glycol around the store. What the pumps must do is be able to overcome the pressure loss or friction in the fluid distribution system. So think our heat exchangers, our piping itself, and solenoids, flow control valves. In this particular operation, or in this particular application, we're using centrifugal pumps, even though there are some other pumps that we could use. This is what we're using. Fluid distribution system, it's all the pipework, balance valves, expansion tank, air separators, any vents and drains. When we're doing this, we're using ACR copper. It's slightly pressurized with and capped off. It's slightly pressurized with nitrogen and has rubber caps on the end. We don't have to use it. It's not part of the spec, but it keeps the system free of contaminants. Most of what we're doing is brazed with silver solder, and then we use soft solder on all brass to copper fittings and potentially nearby. One thing to be mindful of is if you're moving these pipes around, you have to be careful near valves because soft solder cracks really easily, and you don't want to have a bad day if one of those cracks or breaks off. We've got our controllers. We've got the main controller and an EEV controller. EEV controller, all it does is manage superheat, and then the main controller is responsible for pump speed, enabling or disabling the EEVs, managing fluid temperature, and managing alarms. So we're going to go through and talk about these Rae chillers specifically. I have these labeled as version 1 and version 2. There's a version 3 now that looks very similar to the version 2. It's just got some hinge doors on them. Rae will refer to these as Gen 2, Gen 3, Gen 4. They almost exclusively, Gen 1 is a prototype from my understanding, and they won't mention it like that. Going to start getting more detailed about these skids in particular and going to go over each individual component. This is more Rae specific. We're going to start with heat exchanger. So in these skids, it's a 2-circuit heat exchanger tied into the rack. We're going to use it to cool 35% propylene glycol to 20 degrees. This will be a substantial, if not the only load on the existing DX rack. Version 1 uh, has, and version 3 and beyond so far have liquid line solenoids before the chiller EEVs. Version 2 went away with that for a software version, for a software solution, but the newer versions have brought that back. And what I've noticed is getting the meat case, open air meat cases, they seem to struggle a little bit, and chilling the glycol down to 17, 18 degrees seems to take care of that. Then we've got our refrigerant heat exchangers. This one pictured is an older style before they were included with the equipment. What it's doing is it's subcooling the refrigerant going to the rack and increasing the superheat, or I'm sorry, it's subcooling the refrigerant going to the skid and superheating the refrigerant going back to the rack. This is so we can make sure that we provide enough liquid refrigerant to the skid for the EEVs to function correctly. Versions 3 and on all have heat exchangers installed at the factory, so you won't have to do this going forward. And these heat exchangers are like the ones we would normally see on non-subcooled racks, just much larger. These are installed regardless. On the new versions, these have been installed regardless of whether or not the rack is mechanically subcooled or not. So our pumps. So our pumps are 460 volt three-phase pumps. These pumps are controlled by a VFD and operate in a lead lag configuration. The VFD is used to maintain consistent pump pressure between pump suction and pump discharge. Rae Corp is going to refer to this as DP, differential pressure. Because they run in lead lag configuration, there's a changeover between the pumps that happens every Wednesday, 9 a.m. Something to note, these two pumps should never run at the same time. They're each running independently. Then just generic pump. Generically, you don't want to run pumps dry. Pumps will be damaged. There's a low pressure glycol switch that will turn off the pumps. It can either be hardware or software, depending on the version. Here's our VFDs. These are variable frequency drives. And what they do is they utilize an enable signal. What the VFDs do is they take 60 hertz AC power and output simulated AC power at a frequency other than 60 hertz. So in this application, the main Corel controller will close a set of dry contacts, signaling the VFD to act on a 0 to 10 volt DC speed signal with a minimum speed of 30% or 18 hertz. Here's our expansion tank. And what that expansion tank is going to do is it's going to allow for stable pump operation and thermal expansion of the glycol. Expansion tank pressure is traditionally set slightly lower than glycol pump suction and is not piped in line, but off to the side. It's kind of teed in and sits to the side of flow. The exact expansion tank pressure is determined by the application, roof mount versus ground mount. Rae Corp is sets the expansion tank pressure when they come and commission the skid. Next is our air separator. And what that does is separates air and glycol. Inside this air separator, it creates a vortex inside and it causes bubbles to fall out of solution. Those bubbles will rise up to the surface and then get purged out through a auto purge valve that bleeds the air out, and as soon as it's exposed to liquid, automatically shuts. That vent, it has to be the highest point of the separator for it to actually work. So we can't lay this on its side and expect it to work as intended. Here's our Y strainer. Y strainer is just a fine mesh screen. Think of it like a filter. Filters out large particles that could damage pump or control valves. The screens can be cleaned or removed. Version 2 has an additional screen in the suction guide that we're going to talk about next, and that has to be cut out of the way. Suction guide. Suction guide is used to remove turbulence of flow instead of 20 feet of straight pipe. It contains a construction screen that must be cut away. These screens are often missed on startup, and they need to be cut out before you add glycol to the system. The larger screen on there that you can see, that must be left in place because that's what is used to create laminar flow. I'm going to talk about our controllers next. Main controller is our Corel controller. All versions utilize a Corel CPCO as the main controller for the skid. Corel takes inputs from different sensors, including suction, discharge pressure, glycol supply and return temp, and refrigerant pressures and temperatures, and makes some decisions based on that, like signaling the VFD and EEV controllers. The main Corel is where most of the parameters can be changed, and to access this is view 0001 and edit 0002. Then we've got our EEV controllers. In version 1, it uses a Sporlan chiller controller. These are basically non-existent, and they're very similar to the Sporlan subcooler controllers that you'll see, all very similar parameters. Then you've got your version 2, which is using the EXD SH1 from Emerson. You can see the passwords for these are written here. Passcode is 111 for the Sporlan, password of 12 for the EXD SH1 for the Emerson Copeland controller. Both of these communicate with the Corel via Modbus RS485, and you have to make sure that the superheat and correct refrigerant is programmed in both the controller, both the main Corel and the EEV controllers. If the wrong refrigerant is set up, the PT chart won't match, and we're going to flood the rack back and damage the compressors. EEV controller for the third version is a Corel EEV controller. It has a passcode of 0066, and it has some adjustable opening parameters. This is the new one that everybody's going to be using. We're going to want to set the opening percentage up to 15%. By default is set to 50% and will flood the rack out if you're not careful. And then we're going to set the P gain in the PID loop for these to 20. And what this allows the controller to do is operate, or the EVs to open and close more quickly and as superheat changes. So version 2 uses an uninterrupted power supply to close down the EEV on version 2 in the event of power failure. Version 1 and version 3 and on went away from this, and you use liquid line solenoids to prevent flood back in the event of a power failure. So compressor proof, all versions have some version of this, some form of this. Version 1 uses current sensing relays to close some contacts. Version, and for proof that the A compressor is operational, versions 2 and 3 have gone away from this in favor of software, and it locks out the EVs in the event that suction pressure is above 40 degrees suction saturation pressure. And what this is for is to prevent flooding of the rack in the event that all compressors are off. These skids, all of them have emergency service connections, and they're bolt-on flanges that allow the skid to be isolated and a mobile chiller to be connected in the event of total loss of a pump or refrigeration. Here's some autofill stations. They are a 52-gallon reservoir with an integrated pump. And what it does is, in the event that there's low glycol pressure, this pump will turn on and pump glycol into the system. My recommendation would be to leave it off while it's not in use. That way you can identify a leak quickly, and not when you've run out of glycol and this tank's empty and suddenly you've lost 52 gallons of glycol. It's regulated by a pressure switch set to the pump suction operating pressure, and a float switch in the bottom of the pump that prevents damage to the pump in this fill station. These, as far as I can tell, are going away and not going to be installed anymore. What I've done is I have built a field built fill station, and what it is it's a pump very similar to what they're doing with the manufactured one, controlled by a pressure switch. But instead of a reservoir that this is mounted onto, I've made a portal version where we can have it inside of a drum. That drum is full of glycol, and then as we put glycol into the system, it goes and fills, and this drains out of the tank of this drum. And we have to be mindful. I don't have any float switch on it, so you have to constantly fill it. There's a check valve in the bottom of this that prevents draining back into the drum in the event that this fill pump turns off. Next is some flow control components. Here we've got balance valves, end of loop valves, and solenoids. This is going to control flow through our cases and our walk-ins. So the primary and most commonly used valve in these installations is these Hayes auto flow valves, and they automatically control flow within plus minus 10% of what is printed on the body of the valve. And you'll find these on the outlet of every evaporator. You can manually check these valves, the pressure. You can manually check the flow through these valves by taking the pressure differential across the valve and referencing manufacturer's charts. Inside of there's that's a replaceable cartridge, and depending on what flow you need, you can replace that cartridge with one with a different flow rating. One thing that can happen is that little rubber stopper you saw in the last slide, that can become dislodged and get stuck in the return. It's not super common, but you have to know it's a possibility. Next is these Hayes manual flow valves. This is typically for walk-ins. They're a 90-degree ball valve. They're really time-consuming to get set properly, and to set them, you're going to measure differential across this valve and make tiny adjustments to that handle, and it's really easy to make a mistake. As the project moves on, these valves may need to be adjusted as the differential changes as we add more cases, more walk-in, more load. Here's another version. This is an upgraded version of that last manual balance valve. It's a gate style valve, and it has numbers on the dial that we can use to precisely set flow. There's a nice app that you can use that based on the pressure differential across the valve, you can dial in the number to get a precise amount of flow. Same thing, you'll need to adjust these as you go. And you've got your end of loop valve. This is going to be piped directly from supply to return and bypass a portion of the glycol past all loads returning directly to the skid. This is going to be piped either at the very end or 2/3 down the main trunk line. Versions 2 and 3, you must use the 2-inch pipe provided. Anything less is inadequate. Version 1 used an end of loop transducer to calculate flow. Going forward, this transducer has been relocated to onboard the skid and just uses the pump supply, pump return transducers to calculate the differential pressure. Version 3 end of loop valve is one of those Hayes auto flow valves, just a bit bigger, and it does not need manual adjustment like the other ones. One thing to note is these are going together with unions and are prone to leaking. So just if when you're first installing them, be mindful of that and go here first. Start leak searching here. Next is some solenoid valves. They're the primary control for our walk-ins and cases. They're located on the supply of each coil and are typically one per case or walk-in. Spring-loaded, then what they consist of is a spring-loaded rubber diaphragm used to prevent flow and is open via an electromagnet. Our solenoid valves are the most likely place to become obstructed with debris from installation. So when these get obstructed, it's not actually obstructing the valve. What it's doing is it's preventing that diaphragm from seating and stopping it from closing. What's happening is we continue to cool past set point and we don't go into defrost, and it results in iced up coils. We're going to cut the video here because I can only make 30-minute videos, and this going over operation will be part 2.